Depending on the calculation, ethanol has 38% less energy than petrol, or petrol has 63% more than ethanol. Both figures describe the exact same fuel, but the story changes depending on which one you use as the base. The scientific baseline starts with mass energy density. By weight, 1 kilogram of pure petrol holds 44 megajoules of energy. A kilogram of ethanol holds 27. If you use the larger petrol number as the base and divide the difference by 44, the math shows ethanol has 38% less energy. This is the figure typically used in official policy framing. But switch the base to ethanol and divide that same difference by 27. Now the math shows that petrol contains 63% more energy. Statistics can be tilted by shifting the denominator, but the physics of combustion are fixed. To understand how this affects a car, we have to look at how fuel is actually sold. While those previous numbers are based on weight, internal combustion engines don't consume fuel by the kilogram. They drink it by volume. This is the volumetric energy density. 1 liter of standard petrol provides about 34 megajoules of energy. 1 liter of ethanol provides 21. Measured liter for liter, petrol contains 62% more raw energy than ethanol. This 62% energy gap per liter is a mechanical bottleneck. It dictates how a vehicle performs the moment you introduce a blended fuel. When you run a standard engine on E10 or E20, you are replacing high-density petrol with lower-density ethanol. To generate the same amount of force required to move the car, the engine must compensate. It has to ingest a larger volume of the blended fuel to match the energy output of pure petrol. Because you have to burn a higher volume of liquid to travel the same distance, the kilometers per liter ratio drops. This drop in mileage is a direct consequence of the fuel's lower energy density. It's a physical requirement of the engine, regardless of efficiency claims. The engine is effectively forced to consume more fuel just to maintain its baseline performance. Standard engines have physical hardware limits. Specifically, the fuel injectors can only pump a set amount of liquid into the cylinder at any given moment. When you need sudden acceleration or heavy torque, you push those injectors to their maximum flow rate. If the fuel hitting that maximum limit is a lower energy ethanol blend, it cannot produce the same explosive force as petrol. The engine is receiving the maximum volume of fuel it can handle, but that fuel lacks the energy density to provide a punch. Reaching that mechanical injection ceiling with a diluted fuel is what makes the car feel sluggish or unresponsive during a pickup. In a light car on a flat road, these losses might be subtle, but the energy gap is exposed when a vehicle is pushed to its mechanical limits. Consider the structural weight of a pickup truck fitted with a heavy cargo cage. Or look at a large, heavy, multi-axle commercial truck carrying a full payload. When these vehicles climb steep inclines or attempt to overtake on a highway, the engine demands peak torque to keep the mass moving. Under this stress, the lower energy density of ethanol blends leaves the engine starved for power. The performance drop becomes impossible to ignore because the engine cannot draw enough energy from the fuel to meet the demand. Heavy cargo loads strip away the neat statistical framing and truly reveal the physical reality of the fuel blend. The fact that petrol contains 60% more energy than ethanol is not an exaggeration of the math. It is the scientific baseline. Blending in ethanol lowers the total energy density of the fuel in the tank. Regardless of how the percentages are presented, a drop in mileage and engine pickup is a mechanical certainty.